So we shall begin today. If you recall, in the last session, I explained to you what is Unix operating system, what is its architecture, and what all commands you can execute at the shell prompt. Could you get some time to go through the commands?
Yes, sir. Yeah.
Okay. Yeah, so it's a very exhaustive set of commands, but if you have just gone through few of them, that's good. Okay. Today we shall get into the internals of the operating system. In the architecture we saw there is a process management block. So how can I create my own processes? Okay, so how do I create a process in the first place, and how do I communicate between the processes? So inter-process communication mechanisms we have to explore. So process is a program in execution. So it will have its own memory to store its data and its code. So I have pictorially shown you that we can create a process. We can show it as a whole symbol with the arrow like this. It means the program is executing like this. Now this process can give rise to another process, and this process is called as a child process, and the process which gives rise to another process is called parent process. So every process will have an ID. So yesterday we were discussing about PID. So parent will also have its PID and child will also have its unique PID. Let's say this has 697, something like this. This could be 698. So system will assign this number so that you know exactly which is which process. So they are identified through their process IDs. Now, creating one process, what exactly happens in memory? If you recall, in our C programming series, we looked at memory layout of a C program, right? So we had stack here, we had the heap, then we have the initialization segment, DSS, uninitialized segment, then environment variables, and then your program. So a process will be laid out in memory like this. So this is your parent process. So this process, while executing in this part of the code, if it wants to create one more process, then you have to call a system call called as fork. So fork is a system call. It is not a library function, remember. If it is library function, the function you have to write within this and you have to execute. It is a function in the operating system. It is inside the kernel. Okay, so you have to call this fork function. This will give rise to another process. It means it will lay out memory separately from this. So this is the child process. So it will have its own stack, it will have its own heap, then DSS, uninitialized segment, and then its own program. So an exact replica of this will be done. Some part of this will be copied because what is common to parent will be sometimes common to child also. So we shall see what are the things which become common to both and what gets copied and what doesn't get copied. So the child will get its own memory layout like this, and these two processes will execute concurrently. It means some instruction of main will be executed for some time, then the context will switch to this will get executed, and then it will resume executing this, again switch back to this. So depending on the scheduler, for example you have round robin scheduler, then fixed amount of time is assigned to parent. After that time elapses, it will switch to child. Again the time elapses, it will switch back to the parent, and it just goes on until both of them complete. Okay, so this is what is a process creation step. Now one important thing to remember, fork being a system call, this returns twice. Now regular functions we have seen, if you call a function it will execute and it will come back only once, whereas fork will return twice. First time when it returns, it will return a PID value equal to 0, and second time when it returns, it will return a PID value greater than 0. Now using this, we will be able to identify which portion belongs to the parent and which portion belongs to the child, because we'll be in the same program. The program will be same. Let us say we have a program named proc.c. So within this I'll be calling fork, and within this I'll be designating some part as child and some part as parent, and we shall see that happening when I write the code and show you. Okay, yeah. So is the concept of a process is clear? Hello, or you have doubts?
Yes, sir. Yes, sir.
Okay. Yeah, now we shall see how to do all this in a program. Now on the window, this WSL, I have a editor called as Nano. So I just call this Nano program. It will come up with an editor like this. And you need to include these header files. std.h, you are familiar for printf and scanf. unistd.h, it's a Unix standard header file which contains some user defined and system defined types. And there is one more header file called as wait.h. A parent can wait for the child to complete. For that we require this header file. Okay. Now if I want to create a child process and print its PID, and the parent prints its own PID, the first thing that you would do is define a PID variable. So this PID underscore T is nothing but an unsigned int which is defined in unistd.h. Okay, so we know that we can redefine the variables using type def. So that is what is done in unistd.h. Now next thing is I have to execute the fork command or fork system call. Now this fork system call will return twice. First time with PID equal to 0. So I check whether it has returned with PID equal to 0. If it returns with PID equal to 0, in the if block, this is what is the child process space. Even though separate memory layout is done, you can execute the child within the same program. Okay, so here uh, if you want to print the PID of the child, you can do that. So I am child process and my PID is equal to %d/n. There is a function to get the PID. You just have to say get PID. Okay, so this is what the child will print, and in the else part, obviously if PID is not equal to 0, it will be greater than 0. So if it is greater than 0, it means it is a parent process space. So this is a parent process space, and here I am going to again print I am parent process and my PID is %d/n. This can also execute get PID. Okay, and then return 0. So this is the block. If block PID equal to 0, whatever child wants to do, it can carry out. I am just simplistically printing some message. However, you can build some more complex logic here of calculating or finding the first prime numbers and all, and parent doing checking whether a number is prime or not. So you can have different tasks assigned to the parent and child. Okay, is it that one parent can generate only one child? No, it can generate as many child processes as you want. If you say PID equal to fork again, there will be one more child process created. But for demonstration, I have only one parent and one child. Now after this, I have to save it and compile this. Then execute this program. Now we will see I am parent process and my PID is 1472, and then the child executes. I am child process and my PID is 1473. So automatically the PIDs are assigned. Okay, so and then you can check whether the parent of this child process is really 1472. Now to do that, what I do is in the child process, along with the child PID, I'll print the parent PID also, and my parent PID is equal to, if you just execute one more function, get PPID. PPID is parent PID. So in the child I am calling get PPID, it means it will return the PID of the parent. So now, and of course I should put 1 minute, I have to put one more %d, otherwise that parent PID will not be printed. %d. Again I have to compile this and then proc. Now you see that I am child process, my PID is 1482 and my parent PID is 1481, and if you see the parent PID is 1481. Okay, you got the relationship between parent and child. Hello?
Yes, sir.
Okay.
Yes, sir.
Yeah. So yesterday we were discussing, when I type PS, it was giving some PID here. So this is what the PID is, process ID. So the shell which is running bash, which is also a process, and it has a PID of 563, and the PS command which I just ran has a PID of 1483. Okay, because 1481 was used by my parent process and 1482 was used by the child process. The next PID is assigned to the PS command which I ran. So every command you run at the shell prompt will have its own PID assigned. Okay, so PS command is running and it captured its PID, but ls when you ran, it only ran its PID could not be captured. Thing is, it should be running at that time to capture the PID. Here ls had completed the execution, so it could not capture the PID of the process. Okay, so did you understand how to create a process using the fork command? Okay, now next thing is
Yes.
the parent can wait till the child completes. So here what happening is, parent is executing first and then the child is coming up. So I can make the parent wait using the wait system call, and if you want to wait for any process, you just have to put null. Otherwise you have to put the PID of the process for which you are waiting. Okay, so now I just put null because there is only one child process, it will wait for it. Now you will see that child printing will happen first and then the parent will print the PID. Again I have to compile this. Run this. Now you see that the child is running first. Okay, and the parent has waited for it and then it has printed its PID. Did you understand why the print sequences are interchanged?
Yes, sir.
Okay, so there are very useful system calls which help you to wait for a particular PID or wait for any PID, like that. So process creation is as simple as this, right? And threads, when you see, we have discussed threads in C++. Threads, don't create a separate memory layout. They will work in the same process space as the parent. In this discussion also, we shall take up process how to create a thread from a process using the system calls related to the threads. But till that time, we shall only work with only processes. Okay, and processes, that is why they are called as heavyweight uh, objects, whereas threads are called as lightweight processes. Okay, because they don't replicate the memory of the parent when the threads are created. Okay, so this program I'll share with you. Just see how the sequence has to be followed, and you execute the program and see for yourself. All right. Okay. Now, once you know how to create processes, many times one process has to communicate with another process. For example, we have ls command. Now, ls command output should go to another command, either grep or let us say more command. So, the ls command, when you execute with -l, the more command will take this output and paginate and then print. So remember, ls is one process, more is another process. So this vertical line is called as pipe. So this will help the both the processes to communicate with each other. So what is generated by ls will be captured by more command. Okay, so we shall see how inter-process communication happens. Now, before that, one more small thing I missed out, that in the child process I'm just printing this thing, that is the PID and all. So normally you don't create a child process just to print the PIDs. You want to execute another program in the child process bit. For example, if I want to execute ls command, I just have to use execl. So execl is also a system call where I want to run any shell command, let's say ls-l, where you have to indicate where that shell command is. It is in the bin directory. Then you actually indicate what is the command that you want to pass and what are the options you have, ls-l, and then if that is the end of it, you can put a null here. So there are 3 or 4 arguments. So first is the path where ls command resides. Second, third, fourth, they are all options. ls-l or ls minus. You can add more options also. For example, if you have ls-l, comma, you want to print all hidden files also, ls-a also. And only thing is last must be null. It means the options will exhaust here. Okay. Now what happens is child process will anyway run. It will show the PID, PPID, and after that the exec will run the ls command. I am not running ls command exclusively. In the process space of child, the ls command will be executed. Let's see that action. So again I have to compile this and run the process. Now you see that the child process is showing its PID and PPID. Remember, every time you run, the PID is changing because the earlier assigned PIDs will be ignored and the new PIDs will be created. So child PID is having a PID of 15.5 and the parent is 15.4, and it is showing the ls command execution. I did not run ls command, it ran with the exec, and after that the parent has waited for the child to complete and then it is printing its PID. Is this part clear? Hello?
Yes, sir. Yes, sir.
Yeah, you can run any command. It's not always you run ls command. You can run cat command also. You know that suppose we have all these files. If I say cat let's say pipe1.c, you know what cat does? Cat will list this program, whatever is that. Okay, so can I run the cat command in the child process space? You can do that. If you go here instead of ls we just give cat, and this is the cat command, and the argument is which program you want to run. proc1.c, this is not required. Okay, so if I run this, compile this proc, now you see that the child printed the entire file and then the parent showing its PID. Okay, so normally a fork is followed by a exec. Okay, so that is what you should remember. The child processes are created to make a room for running a process, and the process normally runs another program, which may be the system command or your own program that you want to execute. Okay, all right, now this is about process of creating a process. Now let's see how interprocess communication is implemented. So you know how to create a parent process now, and also from parent how to create a child process using fork. Okay, now if these two processes have to exchange some data, then there should be a interprocess communication mechanism. Okay, so one of them is pipe. There are many mechanisms whereby two processes can communicate. Pipe is one, second is message queue, third one is shared memory, fourth one is your semaphore, and last but very important one is the sockets. Now the first four will be within the same machine. The processes have to be running on the same machine for these first four to work. Okay, whereas sockets allow you to communicate two processes running on two different machines. So machine 1 and machine 2 so can communicate with socket, and it makes use of the TCP/IP protocols tag. Okay, so how all this interprocess communication happens within machine and between two machines, we shall see in our subsequent sessions. But today we shall look at how a pipe can be created, and pipe is duplex. It means data can flow in both the directions. Parent can write into this and also read, and similarly the child can read from it and also write to it. Okay, now when you create a pipe, it will return an array of descriptors. So file descriptor will come. Normally two file descriptors will be there, fd0 and fd1. This fd0 is for read and fd1 is for write. It means when your parent creates a pipe, it will have two values in an array. You have to declare an array of type integer here, int fd2. fd1 and fd0 will be used. When you create a pipe, in this you have to specify the array file descriptor. It will come up with the two values, one for read, another for write. Suppose the parent wants to write something to the child. Let's say it wants to write hello world. It has to write to this pipe using the file descriptor 1. What will it do with fd0? fd0 can be closed because it's not required. You can close it. Similarly, this does not require a read end. Write. It doesn't require write end. fd1 can be closed here, and it can read from fd0. And when the message is captured by the child, it can print it. So you have to write this message hello world here using the file descriptor 1, and this will read from file descriptor 0 and it will print it here. Now all this sounds little clumsy and difficult to grasp. We shall see the program and see how both parent and child can communicate with each other. So I will take you to the program right away. So we have okay, so nano pipe dots. Yeah. Okay. So since we have to create two processes, first thing is you declare the PID variable. Then we require file descriptors. Two file descriptors are required. So I store them in an array. You can take two integer variable fd1, fd2 like that. Instead you use this. And okay, you require buffer to hold the data that is coming from the parent. You can give some specific size here. So first thing that you do is you fork it and you check where you are in the process space. This is the child process space, PID equal to 0, else is the parent process space. So this is child process and this is parent process. Now the parent wants to yeah, you have to create the pipe also first. Here you use pipe fd and you have to check if it returns less than 0, it means there is some problem. Error creating pipe. And you just return from this, return 1. If that is not the case, then the pipe is executed, and in the parent, first thing that you do is you close the read end. So you close fd0. See, I told you that parent and child share some variables. So the local variables which you declare here, like the fd, is visible in the child process space as well as in the parent process space. Okay, so in fact it will have a copy of itself. So it is not actually shared, it is copied completely. That fd is copied to child also and parent also. So when I say fd0, it is the copy of the parent, and if I say fd0 in the child, it is a copy of the child process. Now after this I define one more message here, is equal to, let's say, today is Friday, some message, and this message I want to uh, pass it on to the child. So you just have to say write fd1 the message, then length of this message plus 1, because that one extra character has to be passed. So what parent has done is it has written the message, and here it can close the right hand also after doing its job. I am not printing the PIDs. Now what the child has to do? Child has to close the read end and it has to read from the it has to close the right end 1 year, and it has to read from the read end fd1 fd0. And whatever that has come, it has to print it. I am child received message from parent percentages. Okay, so the program is all about establishing parent-child relationship, and parent is writing to the child and child is reading from the parent and displaying the message here. Okay, so hope everything is correct everywhere. Now let's try to compile this program. gcc pipe dot c minus o pipe. Okay, so there is a spelling mistake, line 43. Close, close here. Okay, now if I run the pipe program, you will see that I am child received message from parent. It's not displaying the message. Okay, we'll see what is wrong. Write fd1. So can have wait here. Still it's not working. Just a minute. I will just check the correct version of it. Pipe1.c. Period equals 0. Close fd1. Close fd0. Everything is same. Here equal to fork. One minute. Both are same actually. I think so this pipe will return -1. This should be -1. PID close right end, read fp0 buffer, size of buffer, percentage, yes, okay, close the read end, write fd1 message, message 1, close fd1, so correct. gcc pipe dot c minus it's not still having some problem. Okay, so I have the same problem in pipe 1. So let me compile that gcc pipe 1 dot c minus o pipe 1 dot slash pipe 1. Okay, so received from parent hello world, I am parent. Only thing is I am displaying a separate message here. So if I want, I can change that nano 1 dot c. Instead of hello world, I can just change this message to today is Friday. I don't know where exactly the mistake is, but gcc pipe 1 dot c minus o pipe 1 dot slash pipe 1. Now you see received from parent this message today is Friday. Okay, so how exactly it is doing? It is simply creating a pipe and creating a process. In the child process, it is reading the message which is coming from the parent. In the parent process space, it is closing the read end and writing to the right end by passing the message and its length and closing FD and waiting for it. I think so. Only problem was that fork was done before the pipe. That is where the mistake is. I think so. If I interchange the two, it should work. This step, because the moment to create a child process space, everything will change. This should happen here. PID equal to fork. The pipe should be created after, and then the fork should be done. I think so. That is the mistake. Let us see. gcc pipe dot c minus o pipe dot slash pipe. Yeah, it's working now. Okay, so only mistake was I was creating the process and then creating the pipe. That is wrong, because the process should come later. The pipe should be ready and pipe should be shared between the child and parent. So if you create a child process before the pipe, then the pipe FD will not be shared with the child. So first thing is you must create the pipe data structure and then create the process. That was a mistake. Okay. So did you follow what we have done today? Hello?
Yes, sir. Yes.
Or it was all confusing?
A bit, sir.
Yeah, a bit confusing. I'll share the code with you. Just go through because to get familiar with the use of system calls. So can you identify the important system calls here? Which is a system call? Any one of you?
Four.
Fork is a system call. Okay. Likewise, any other?
Five.
Pipe is also system call. Your read is also system call. Close is also system call. So many system calls are there. Okay, so they all look like your library functions in C, but they are executed in the kernel space. Even the way it is a system call.
Is
Is
close
close
also?
also?
Yeah, close also is system call. Because see, imagine there is a shop, and there are some very valuable items inside the shop. You cannot allow every customer to get into the shop and take anything that you like in a shopping mall. In a normal conventional shop, the shop owner will be there. He will ask what you want, and then you will get it, and after your payment is made, the item will be given to you. Just like that, operating system has to protect itself. You only ask what you want. The operating system will take your commands, you will do the job and come back with the result. So here you are asking the system to create a child process using fork. So it will give you the PIDs, that is the outcome, and then you work with it. Again, when you want to work with the kernel resources, uh, you have to use appropriate system calls only, like the pipe that you created. User process cannot create a pipe because the pipe will be residing in the kernel space. And to write to the kernel space, again you require read and write, which are again system calls. Okay? Yeah. So I'll share this code, experiment with all that I've explained to you. Get familiar with writing programs in the Linux environment. And the editor that you can use can be a VI editor, which is very clumsy and very difficult to learn. Best thing is Nano or gedit. So there are couple of editors available, like gedit. If you do, it will come up with a visual editor like this, and here also you can write the program. Okay, of course you don't get any context help. You have to type all the program yourself. Okay, so gedit can be one of them. If you don't find nano or gedit, you have to say you have to install this. So sudo apt install nano. If you do, the editor will be installed for you. Or if you want gedit, you can install gedit. VI will come by default. Okay, but if it is not installed, again you can do VI. So I would suggest you to install nano using this command, and using the nano editor you do the programs. All right. Okay, so we shall close for today, and in the next session we shall look at message queue, shared memory, and other IPC mechanisms. All right.
Sure,
Sure,
sir.
sir.
Okay then. Bye.
Thank
Thank
you.
you.